If you work with modern count data, you know the exact shape of the problem. You have a matrix of non-negative integers. Every row is a sample, every column is a feature, and the total count per row is fixed by sequencing depth, sampling effort, or user attention. The data is sparse, heavily overdispersed, and fundamentally compositional. Yet almost every normalization pipeline you use either ignores the joint structure, destroys sparsity with pseudocounts, or treats features as independent when they are mathematically locked in competition for a fixed total. Today, we are going to walk through a new normalization framework that solves exactly this problem. It is called the Dirichlet multinomial deviance residual transform. It is sparse, it is likelihood-based, it scales linearly with the number of non-zeros, and it comes with a clean theoretical interpretation that connects joint compositional modeling directly to feature-wise negative binomial regression. More importantly, it works as a drop-in replacement for downstream tasks across single-cell genomics, microbiome analysis, spatial transcriptomics, natural language processing, and even recommender systems. Let's start with why the standard approaches fall short. When you condition on the row total, the multinomial distribution is the natural joint model. It assumes that once you fix the total, the allocation across features follows a rigid probability vector. But real data is rarely that clean. Repeated counts happen more often than the multinomial predicts. This is overdispersion. If you try to model it feature by feature using independent negative binomials, you fix the overdispersion, but you break the compositional constraint. You lose the fact that an increase in one feature must mathematically compete with decreases in others to keep the row sum constant. The Dirichlet multinomial sits exactly between these two extremes. It is a joint, fixed total model that adds a single scalar degree of freedom to control overdispersion. But how do you actually turn this distribution into a practical normalization transform? The key insight is how you define the residual. In classical deviance calculations, you compare your fitted null model to a saturated alternative. If you let the Dirichlet multinomial refit both composition and dispersion for every sample, the optimum collapses back to the empirical multinomial, and you lose the overdispersion correction entirely. So we fix the concentration parameter. We keep a single global overdispersion scalar, let's call it alpha 0, and we only allow the sample-specific composition to match the observed row. This gives us a closed-form, sparse transform that evaluates in constant time per non-zero entry. Let's look at the math behind it. For any non-zero count, the residual is assigned square root of an additive log likelihood contrast. It compares the probability of observing that count under the global null composition to the probability under the sample's own empirical composition, while holding alpha 0 fixed. The result is elegant. For singleton counts, the DM residual is mathematically identical to the multinomial residual. But for repeated counts, it applies a smooth shrinkage. The amount of shrinkage is directly controlled by alpha 0. As alpha 0 goes to infinity, you recover the multinomial exactly. As it gets smaller, the model discounts heavy-tailed repeated counts that a rigid multinomial would treat as surprising signal. There is a deeper statistical reason this works so well. If you model each feature's count as an independent negative binomial with a common success probability, and then you condition that joint distribution on the observed row sum, the resulting conditional distribution is exactly the Dirichlet multinomial. This means the DM residual is not just an ad hoc fix. It is the exact joint conditional analog of the feature-wise negative binomial residuals that dominate bulk RNA-seq pipelines. The difference is that the DM respects the compositional geometry from the start. Computationally, this is a massive win. Because the zero entries contribute exactly 0 to the score and the Hessian, you only need to iterate over the non-zeros. The transform preserves the exact sparsity pattern of the input matrix. There is no densification, no pseudocount inflation, and no fill-in. The wall clock time scales linearly with the number of non-zeros, and the constant factor is only about 14 times that of a simple log 1 plus transform. That is fast enough to run on Atlas-scale datasets without breaking a sweat. Now, what about structure? Real data rarely lives in a flat, unordered feature space. In microbiome studies, features are organized by a phylogenetic tree. In spatial transcriptomics, spots are arranged in a geometric grid. The DM framework extends naturally to these hierarchies. For ordered features, you can use the generalized Dirichlet multinomial, which models sequential allocation with stage-specific dispersion. For tree-structured data, you use the Dirichlet tree multinomial. This factors the likelihood node by node, allowing broad taxonomic splits or spatial regions to have their own dispersion parameters, while fine-grained leaves remain tightly constrained. The result is a multi-scale residual representation that is sparse over branches rather than leaves, and it dramatically improves taxonomic coherence and spatial continuity without requiring ad hoc smoothing. I want to stress how this performs on real benchmarks. Across single-cell UMI data, chromatin accessibility, and antibody capture assays, the DM residual consistently improves held-out conditional log likelihood over the multinomial baseline. More importantly, it fixes a critical calibration problem. When you run a parametric differential expression test, the multinomial and analytic Pearson residuals are severely anti-conservative, inflating false discoveries by 3 to 4 times. The per-gene negative binomial halves the inflation, but does not remove it. The joint overdispersion model of the DM, however, calibrates the test exactly at the nominal level. It separates technical sampling variation from biological signal without washing out the neighborhood geometry. And this isn't limited to genomics. In natural language processing, word counts exhibit the same burstiness. The DM residual outperforms TF-IDF and shifted log preprocessing on document classification while preserving sparsity. In pooled CRISPR screens, the DM posterior shrunk log fold chain ties the top hit calling performance of standard MA-GCK pipelines while avoiding the dense matrix explosion of feature-wise negative binomial residuals. Even in recommender systems, where user-item interactions are overdispersed count matrices, the DM residual matches or beats log1 plus and TF-IDF on top K ranking metrics, while providing a proper likelihood-based estimand and superior stability under data thinning. There is one more piece of theory that practitioners should know. The in-sample likelihood ratio you get from the residual transform is a generalized likelihood ratio, which means it is not a valid test statistic on its own. But by splitting each row into a training and evaluation half using binomial thinning, you can construct a split likelihood ratio E-variable. This gives you an anytime valid finite sample test for the global null that does not rely on asymptotic chi-square approximations, which notoriously break down on sparse counts. It composes cleanly with conformal prediction and sequential screening pipelines. To wrap this up, the Dirichlet multinomial deviance transform is not a silver bullet for every modeling problem. If you need to capture arbitrary covariance structures on log ratios, or if you are building a full Bayesian hierarchical model, this is not it. But if you need a normalization that is likelihood-based, compositionally coherent, overdispersion-aware, exactly sparse, and computationally lightweight, it is the natural default generalization of the multinomial. The single concentration parameter acts as a robust regularization dial. The downstream geometry is remarkably stable across a 100-fold range of alpha-0 values, and the method integrates directly into any pipeline that already uses multinomial or negative binomial residuals. If you want to dive into the derivations, the fitting algorithms, or the full benchmark suite across microbiome phylogenies, spatial grids, and NLP corpora, the paper and code are linked below. Normalizing count data has been stuck between rigid compositional models and independent feature-wise approximations for too long. This framework finally bridges that gap with a single, elegant transform. Thanks for watching, and I'll see you in the next one.